Hello, do you hear me here? Yes. Hello, do you hear me here?
Yes, but with some echo.
What about now? Is it better now?
Yeah, no problem now.
Okay, very nice. Thanks. Okay, let's wait for 2 more minutes to see if more people are entering. Okay, see you now. Okay, so let's start. Let me turn on video. Do you see me as well?
Yeah.
Okay, good. Okay, so today, the idea of today is to have the hands-on session on neural nets. So let's go for it. Let me just share screen. So if you remember the yesterday, well, day before, we were okay. We were obtaining how to train a neural net in the context of classification. So we were using the cost the cost function to be the cross entropy, and then we were, by using gradient descent, what we were doing at the end of the lecture was to to obtain the derivative of the parameters. I mean the derivative, sorry, of the cost function of the cross entropy with respect to the parameter. So what we are doing now is to implement, so in the context of a classification problem, we implement these formulas in order to train by hand the network, right? So I have taken the same data that we were using in the case of naive Bayes. So it is written here, but so either you take it from that notebook, or I give you time for writing it if you want. So it's just generating some data with the let's say 2-dimensional parameter space, or the number of features, x1 and x2, 3 classes we are going to use, and then we will put ourselves in a data set which is balanced, in the sense that all the classes will have the same number of points that you can set here in class parameter. They took 500 points per class. Okay. So this is the data set. So please tell me when you have it, because I am I'm working on this data set. So either you just copy paste from naive Bayes or just write it in a second. Note that this is here getting points or sampling points from a random normal distribution where the variance is 1. And we would later do what we did in naive Bayes, which was also had to do with the part of the homework, which was generating different class of points with different variances. Of course, they are centered at different points. Otherwise, you don't have a discrimination, right? If all the classes are centered at the same point, there is essentially no discrimination power. So, but at some point later, if we have time, we play again with the class of points that you generate, and that you have different variances for them. It was with this parameter here. I think, sorry, I think it was this one. Yeah. So right here you can. So by doing this line instead, you can actually specify the variance here. Is there any question so far, or is anyone not having this right now? Okay, so if this is the case, then I continue. So I'm just explaining what it was here. So I'm just stacking here points of class A, B, C, and then I am building my output to be an array of zeros and an array of ones and an array of twos, consecutive arrays, each array with the length equal n class, because classes are equilibrated. And once I plot this, I get this shape. Let me just run this again. Okay. Okay, so now I have
Can you
written,
show for a moment again the code? Because
yeah.
I think the points are generating. Okay, I found the error. Thank you.
Okay, so then let's implement from scratch. So first of all, we will do as we did for classification hands-on. So we implement the model from scratch, and later we will compare with the out-of-the-box model from Scalearn. But first of all, let us implement this from scratch. So let me just put here neural net from scratch. This is one hidden layer. and here is just some summary of the theory behind it. So if you remember here, what the neural network is a probabilistic model, in the sense that the output can have this interpretation. The output of the network is given the interpretation of the probability of class CK, given some data and given some parameters. And then, if this is the case that we are doing a classification, we are facing a categorical variable with this corresponding distribution, and consequently the likelihood is this one, the likelihood of a categorical data if you want. And so where this is the output of the net, and the exponent here t ik are the labels. So it's the label of point I class k in this one-hot encoding parameterization. Remember that. And then you need to multiply over classes and over points, of course. So in order to maximize this likelihood, it is equivalent to minimize the minus log of the likelihood, which is actually the cross entropy cost function, which is just this expression here. Okay. Yes. So let us first of all write the measure of performance here. We can take as a measure of performance the classification rate. The classification rate will have two arguments. First of all, the matrix of predictions. The matrix of observations, let's say. And this is a matrix because you have n points and you have k classes. So this is an n by k matrix. And my predictions should be also the same shape. Okay, so how do we do this? Okay, let me just initialize a variable which is number of correct points, total number of points. And then for I in range, what is the range? It's just the number of rows that can be extracted in this way. For I in range, the number of rows, let's say, so I am having a loop over the rows of the data set, over the points. Then, of course, in total, I increase it by 1. And then what do I need to do is to say, okay, if the observation I is equal to the prediction, the corresponding prediction, then n correct is increased by 1. Otherwise, do nothing. And then I just return the fraction of it. So let me call this incorrect over in total. And then I am, by writing this expression like this, is just computing what is the fraction of correct points, of correct prediction, let's say, for a given number of points whose observations are y here. And we run this, okay? Okay, so let us at this point, or we can do it before or after, but let us at this point do the data preparation, which is just splitting the training and test. So extracting from the original data set, which is this 1500 points, I will split them in training and test in a random way. So there are many ways to do that, and even in sklearn, there is a library for that. But I just use the same thing in my work. Which is just I do it by hand, but it's just a code that I copy paste every time. So let me define. In order to do that, let me just define a random permutation of the data, which is actually shuffling indices from 0 to the length of the input minus 1, but with indices shuffle, right? So by doing this, you see what is this, right? So it is just a random indices that go from 0 to length of x minus 1. Okay, so once I have defined my permutation, I will shuffle the input like this, Because you remember that the way we constructed the input was an order data set where you have 500 points belonging to class 0, 500 points later belonging to class 1, and at the end 500 points belonging to class 2. And now by doing this line, I'm just shuffling, randomly shuffling the data set for the input and also for the output. Okay, my output here is T. This is just a notation of bishop, where T is from true output, let's say. Okay, so once I have shuffled my data set, then I define what is my test size. So typically you have something like, I don't know, 30%, 20%, something like this. So let us take 20% of the whole data set. Okay. And then I define the test as the first 20%. And I define, let me also put here the output. The output is T. And then the train, right? The train is the rest. The 80%. It's train, I think I put this. Anti-train. And this is just from this position to the end. Please interrupt me if there is something which is not clear. So let me just do this, and I check, for example, the X train. What is this? Okay, so it worked. So X train is just same shape. So let me put shape here. Okay, so the shape of X train is just 1200 points with 2 classes, which is the 80% of 500 of 1500. Okay. Right. So once we arrive at this point, then let us start building the network. This is just an image of. This is just a cartoon here of the thing we are going to build. So we are going to build a one hidden layer neural network, having here 3 outputs instead. Okay. And you remember from the previous lecture that you need to go from the input to the first hidden layer, and the output of this first hidden layer, or the unique, the only one that we have here, is just a nonlinear function f of a linear combination of the input, which in matrix notation was just this one. So it's just a nonlinear function of x times w plus b, which is the intercept or the bias or something. Okay, now let us randomly introduce some matrices for w and b, and we do it randomly. Let's say we do a random initialization of this. So I don't know. Let me put a random seed here just to try to make this reproducible. And so we have already a number of features and number of classes. So I don't need to define this here. F and K are already defined. Sorry, I went too far. But now what I need is to define the number of hidden layers. This is the number of hidden units. Number of units in the hidden layer. And let us put this, I don't know, let us start with a small number, just 5 neurons in my hidden layer, 5 units. Then I can say, okay, let me define a random matrix, and this is going to be like the random value, initial value of this matrix, which, so then it's just random dot. So I am saying that the distribution of this, I'm sampling from a normal distribution, standard normal distribution, which means mean 0 and variance 1, but having dimension f by h, right? So you see it from here, no? That the dimension of the correct dimension of w should be the number of features times so by the number of hidden layers. Please, if there is any question, just tell me. Okay, so by doing this, I am, let me just check it. This w, what it was. Okay, so it is a 2 by 5 matrix with random numbers, and they are supposed to come in from a standard normal. Okay. And then the bias, remember that the bias was a quantity which was common to all the features. So the bias is just here a vector. So there is one for each hidden for each unit in the hidden layer. Sorry. Okay. So in reality, when one takes a look at this, bias should be the same dimension as this one, and the dimension of this object here, the multiplication here, is n by h. So why not put in here n by h? It is because when I write the model, NumPy will understand that if I sum an n by h matrix and then I add an h vector, it will understand what it's doing, which is converting this to a matrix with n identical elements and the same. So I am just repeating for repeating n rows the same thing, which is h numbers. Okay. Okay. So let me just test b here, and b is just okay, 5 numbers, 1 for each unit in the hidden layer. Okay, so I have initialized the parameters here, but I need to, in order to define what is z, I need to define what is my f, no, my function, my nonlinear function, and let us use a sigmoid function, because this is what we worked with in the lecture. So it was very popular at the beginning, but now it's less used. But okay, in any case, it's giving reasonable results here. But so let us program this this function. So just this is just the graph of the sigmoid. So you have seen this in the lecture. So then by choosing the sigmoid, we can write the z, which is the output of the hidden layer. So z here, it is going to be a function of the input of the w's and of the b, and I just return 1 over, well, I'm just trying to build a sigmoid here, which is 1 over 1 plus exp of minus, and then I have x dot w, which is the matrix product of x and w, minus b. No? So this is a way to implement sigmoid here. And let us check it. It's always a sanity check to see whether this is, for example, for train, W is already defined and B is already defined, and I think I put it in capital. Yeah. So this is giving me something, and this something has shape, should have shape n by h. Yeah. So n is number of training points by h, which is 5 in this case. Okay. Fine. So is there any questions so far?
Brian?
Yeah.
Sorry, just going back to something very simple, but I was finding it a lot of time, so it's not very related to the neural net. So you use your own very simple permutation function to do this, the data splitting. As you said, scikit-learn and other software have other things. So is this just a lazy way not to write the permutations ourselves, or there's some advantage on using these sort of partitions that are sort of smarter than what we can do?
No, I'm just trying to do at least for you once in your life things from scratch.
Mm-hmm.
So this is just a way to understand what is a permutation doing. But if you understand it, you are free to choose any library you want.
Right, but those libraries have any advantage of, I mean, because in principle, our hypothesis is that the data are randomly sampled. So there should be no advantage on what you're doing over these libraries. So I want to know if these libraries have any like bonus by using them.
No, this is correct what you say.
Okay, thank you.
Yeah. Okay, so what I was doing is to check the output of the first of the hidden layer, which is should have correct dimensions, which is number of points by number of units in the hidden layer, and this is the case here. Okay, so once we have defined the output of the hidden layer, we move to the output. So remember the output we for a multi-class classification, we were motivating the use of a softmax function, which is just this one, this function here. So there is an output for each class. So then for each class, small k. So you have a different output, and of course, if you add all the outputs for a given point in your data set, you should have one actually. So here the argument of the softmax can be written in matrix notation as this. So this is just the output of the hidden layer Z times some other weight matrix V plus some other intercept, the final one, which is C. Which are the parameters, also the parameters that you need to learn. So you remember that there were these 4 parameters: W, B, V, and C. So let's say in the same way we did for W and B, we do it for V and C. So this is just I'm just initializing randomly V, which is a matrix of dimensions h by k. And in a similar fashion, I can initialize a matrix, a vector of intercepts with dimension k, and the same thing that I commented above applies here. When I add this vector to a matrix which is n by k, it will just produce the same row, I mean identical row n times. Okay, so I think this is it. Let me just check it. For example, what is V? V is just an array of 5 by 3 because I have 3 classes and 5 units in the hidden layer. Okay, and then we have everything to build the output. So the idea here is to implement the softmax function. So the output is going to be a function of the input, of course, and of all the parameters of my model. So the parameters were W, B, V, and C. So then the output is just the softmax of some argument, and the argument is A. This matrix A that is written here above. So let us just write this in a convenient notation. So Z, which Z, I'm using this function here, the same Z. So Z actually is a function of X, W, and B dot what? Dot V, no? Because of what is written here above, plus C. And NumPy is understanding this writing in the sense that the writing is producing a matrix which is n by k. This is the dimension of the final output. So then, in order to build the softmax, I will first build the numerator. So the numerator is just the exponent of this A, and this is just that. So in NumPy, which is quite convenient, the exponent of a matrix is just a matrix with elements being the exponents of each element. Okay. So this object has the same dimension as this object. I have the numerator, and then I have finally y is this numerator divided by the sum. So I have to normalize overall classes here. So let me just write XA sum over the second axis. So axis 0 is the rows, axis 1 is the columns. So I need to sum over all columns, which are all the classes. But let me just do this because I need to keep the dimensions in the sense that this should be the same dimension as the numerator. Okay. And then I return y. So let me check this function here. So let me, for example, checking it for a test input. W, I have defined it. B, I have defined it. V and C as well. So let me see what is this producing. This should produce something which looks okay with shape. What is the shape of this? 300, which is the 20% of 1500 by 3, of course, because you have 3 classes. And what I'm saying is that for each row, this number should add up to 1. Should be 1. So let us check this. Let us check that for a random point. For example, this point. Let us check that sum is 1. Okay. So I think this is like a sanity check for this function in the sense that it should produce probabilities, right? Probabilities are normalized. Okay, is there any question so far? We have already built the output of a one hidden linear network. And now what remains is just to train this model. No question. Okay. Is there everyone at this level now?
Yep.
Okay. So let us train this thing. In order to train this, we will use the cross entropy as a cost function, and you remember from here where it was. Yeah. So we'll need to write this cost function here. And there is a very compact way, which is quite convenient for doing this in NumPy. So just take a look at this. It's just the elements of a matrix T, capital T, of the true outputs, the observations, and the log of the elements of another matrix P, which is also I by K. I mean N by K. So I can, this function here, I can write it in a very compact way in the following here. So cost function is as the arguments the true output and the prediction, and if I just do the element by element multiplication with this symbol times the log of my predictions, then I will have a big matrix which is N by K, and I need to sum over rows and over columns. So then I just return, and then the minus sign here, of course, the sum of it, and that's it. I mean, this should produce a scalar, because this method here, sum, is just if you don't specify the axis, it is just summing over all elements, rows and columns of your array. So let me check. Let me check this function. So what is the cost of, for example, T test and the output of this? I will take this output. Without any training at all. This is just with the random point in the parameter space that I have defined here. And okay, let me just see, what is this? Okay, yes. So this is because I need to convert first. Okay, let me check this cost function later, because what I'm doing later is to convert the output. It should be a matrix, but now this is just a vector which has 0, 1, and 2. Or we can do it now. So let me just go a bit forward on that. Let me put this. Let me put the labels in a matrix form, because for now T is not in a matrix form, but it's just a one-dimensional array. So I want to one-hot encode this, and again there is a library for that in Sklearn. I think I am using always my own way of doing it, which is the following. So if I define this matrix to be a matrix of zeros, this matrix of zeros could be. So what are the dimensions? I'm looking for a dimension length of t-test times k, right? If I do this, data type not understood, so no. So here, sorry. Okay, so what is this now? Yeah, the notebook you sometimes put in a parenthesis without me saying it. So T is just a matrix of zeros. So I have initialized my output in a one-hot encoding way. But now for I in range, let's say, now I need to go over all the points. I just say that the element, the ith element, with the I column, with the Ti column, this is equal to 1. And that's it. You see? And that produces this in 2 lines, essentially, produces the one-hot encoding version that I was looking for. Okay. So let me now, I think I'm now in position to test my cost function. So if I go T, and then I go and I try again with this, it is producing a scalar, which is what it should. Okay. Let me just put here t-test because I am later on. Okay, so we have now implemented our cost function. And how do we train the thing? So we need to minimize this cost function, but this is a cost function whose minimization is not analytical, of course. So as we were discussing the day before, we were just using some technique which is here, gradient descent. This is actually probably the same image I used in the lecture. And just a reminder of gradient descent. It is just for a parameter alpha here. Alpha are all these parameters here. So the matrix elements of all my weight matrices. For a given parameter alpha, alpha PQ, I mean the element, the epoch I+1 is updated by the value in the previous epoch minus a learning rate that could depend on the epoch, but here we are not using this. We are using a constant gamma here, learning rate, times the sum of the times the derivative of the cost function, which is the sum over all the elements of the cost function differentiated with respect to the element, the parameter, right? So note, this is a good moment to note how many parameters we have in our network, this counting of degrees of freedom, this counting of parameters. So we have the matrix W, which is a matrix of F by H, plus we have the bias of, so this B of the first layer, which has only H distinct elements, different elements. And then we have the matrix V, which is H by K, and the bias, the final bias, which is also K. So if you put here dimension 2 and the H equal 5 or 5 hidden, so 5 units in the hidden layer, I've got 33 parameters. Okay. So I am using a model with 33 parameters in order to fit the above clouds of points. This is, of course, the case of a fully connected network. It doesn't have to be the case for another type of network. For example, in convolutional networks, the parameters are less because you're not using all the, it's not fully connected. So you don't need a weight or a parameter to connect every element of the previous layer to the element of the present layer, right? So what we are doing finally is to code by hand the results that we were obtaining yesterday. So yesterday we were the day before we were obtaining the derivatives of the cost function with respect to each of these parameters, and the first one was the derivative with respect to the w's, which are the weights multiplying the input, and we have obtained this expression here. This expression here, I think I put it also in the lecture, but there's a much compact way to write this. I mean, you write it in the matrix notation, and so the derivative of this will depend on the input, will depend on the output of the hidden layer, will depend on of course, on the on T, so the matrix of outputs, on my prediction, and on V. So I have just written here in the argument all the elements I see in this expression. So then let me just put here pre-result or something. And then the compact way is the following. So I have T minus Y here, which has elements, so N and K. So this could be multiplied by, so you see this second element here is like having the matrix V, but transposed. So this is just a way to put the transpose of the matrix. V dot T is a transpose of V. And it is because this particular ordering here of indices that I have in the previous expression. And now that will produce a matrix which is N by H. And you see, this is exactly the dimensions of this final object here. But this part is a element by element. This Z NH multiplied by 1 minus Z NH, it is just an element by element multiplication. So here I'm just putting this in a very compact way as this. So I have the first part without the X, without the final X. And then I will return. So you see here, this is an N by H matrix here. So then in order to multiply by X, I need to multiply in the following way. If I take the transpose of X dot the above result, then the transpose of X is F by N, which is then multiplied by something which is N by H. Sorry, N by yes, N by H. Right, which gives me something which is, so the dimensions of this, no, here, so the dimensions of this are a N, so F by H, which is the same dimensions of W, actually, so it is what it should be. Okay. So this on the one hand, on the other hand, I need to do the same for the bias. And if I do the same for the bias, then I will, so if you remember from yesterday, we had a similar expression as this one, but without the final x here. And it is just because I am differentiating with respect to v, which has coefficient 1. So the derivative of b is very similar. So it is just not a function of x. So I have these arguments here. And then it is just one line. So let me write first y, so t minus y dot v transpose times z times 1 minus z. But then there is a sum over n here. And if there's a sum over n here, I need to sum this at some point. So I sum it as, I can do it the following. If I do this, sum over x is equal to 0. Okay. This is a 0 axis because this object here is the first axis is n actually, right?
Didn't we have a sum over n in the last one also? Or am I missing something?
Sum over n. No. Why? Yeah. Okay. So n is so. Let me do this step by step probably. So t minus y has dimension n by k. Okay. So there is a sum over n. By doing this product, there is a sum over n. I don't know if you see it.
Okay, okay. Now I get now, yeah.
Yeah. However, here, since you don't have x, I need to do it. I need to sum it explicitly. So so this is the way to do it with derivative b, and now I have the two other matrix of parameters. Derivative b is just this expression up here that we obtained yesterday, and again we will put this in a very compact way. So derivative of v is a function of z, of t, and of y. So it is just very simply the transpose of z dot t minus 1. It is just this thing. And by doing that, again, here you sum over n, because it is the internal index in the matrix multiplication. And finally, the bias of the external bias, let's say the one going to the output, it is just it is even simpler, and then this is just a function of t and y. I don't need z for this, and this is just this sum of this sum of t minus y. Okay, so now we choose a learning rate because we need this is a hyperparameter of our implementation if you want. Let us choose, I don't know, learning rate, a common learning rate of 10 to minus 4. And and then we go to the fit function, which is the largest one, but it's not that large. So let us finish. So let us go to the break now. I'm just putting the number of epochs or the number of iterations, whatever you want to call it, for the gradient descent method. Let me put 3,000, and then we will see it. And if there is no question so far, I prefer to write the fit function after the break, and we can have, I don't know, let's have it is early, so let's have 10 minutes of break if you want.
Okay, thank you.
Okay, so we go back at 7 past. Okay, so let us start. Is there any questions so far? No. Okay, so let us finally write the final function, which is fit, and the fit is just here. The function where you update the values of the parameter. So fit is a function of everything essentially. So of input and labels, and of all the parameters, right? But also on gamma, where gamma is the learning rate. Okay, so here I'm just let me extract the number of points from the number of rows in X. Then this one hot encoding thing, let me just copy paste from above. I need to one hot encode T. So T is initialized by n by k. Is it correct now? Okay, n by k, and for I in range n, I just say T, the ik element of T is 1. Okay, so then I am updating the weights. So then this is where the training happens. So for epoch in range of n epochs, I have n epochs, I have just here above, I have defined it. Do the following. First of all, let me take the output. Sorry, output equal. All this is the prediction of my network for a given input and parameters, like this. And also hidden. This is just the Z. This I need. Right? Because now I am updating all the parameters. So let me update first I don't know, V. I have here V. No particular order, which is a value, the initial value plus gamma times the function that we defined, the derivative of V that we defined above, of hidden T and output. Okay, remember this derivative V had these 3 arguments. Then I do the same with C. It's updated as gamma times derivative with respect to C. And the derivative with respect to C was just simple, was just, it is this thing above. So it's true output and the prediction, which I call it here output. So let's continue with W. Derivative of W. And W had has arguments X, Z, which I call here hidden, T, which is the labels, prediction, which I call here output, and V. So X, H, so X, Z, T. Yeah, I think this is correct. X, let me just check. X, Z, T, Y, V. Yeah, okay. And finally, the inner intercept. Very similarly, derivative respect to b, and the arguments of this is t, output v hidden. Okay, and that's it. So now what I want to do is to print, because I want to see how the training is going. So let me print here. But I don't want to print for all the epochs, because if I have 3,000 epochs, this is going to be very long. Let me just print every 100 epochs. The way to do this like this. So every 100 epochs, I just see how is it going, the training. So let me just compute the cost function t output, and here I will make the prediction, and the prediction is just the Rmax of all my outputs. So if you remember, the output has 3 columns, and the prediction in a multi-class classification is just the class with the highest probability. So that's why it's the Rmax over all the columns, over all the classes, with which I finally can compute a classification rate. This is the first function we defined above, TMP. So there is a prediction for every point of my observations, and the true value is t, let's say. And let me just print this epoch. Let me call this epoch cost function. Here I write cost, CO. Classification rate equal R. And I think this is it. Okay, so then I have everything. Yeah.
Shouldn't it be indented inside the for to work?
Yes, sure, yeah. Yes, thanks. Oops.
No problem.
Absolutely. Okay, so thanks. So then let me forget about this. Then let us try all this. So I have defined X train and T train, and then I have remember here, initialize these values for the parameters W, B, and the same for the rest. All these values have been initialized above, but then I am just updating these parameters V, B, and C with the learning rate that I defined here, 10⁻⁴. And let's see what it does here. Okay, so it is printing every 100 epochs. The value of the cost function is this one, and classification rate is at the beginning is very shitty. I mean, it's 30%. But it immediately increases with the epochs, so it is already 93 by the first 100 epochs. And actually, you see that it gets to be 96 all the way down. So which means that I don't even need 3,000 epochs here. For the learning rate I am choosing, I may be well with I don't know how many it was. 1,000 epochs is already good. Okay, or if you want, I don't know, 2,000 epochs at most. So one thing, okay, and then let's finally compute what is the cost. Sorry, what is the score on that? So let us compute the score on the test cells, right? So score, I think we also wrote it above. T-test. So let us see what is given. T-test score is not defined.
I don't think we defined the score.
We didn't. Okay, sorry. Yeah. So let us define further score. So def score. Let me put like this: t-test, x-test, t-test. So output test is just the output as before. W, B, and C. So remember that these guys are global variables. Okay, so they are being updated with the fit function, but they are global variables. The way I have programmed this here, I have coded this, and hidden. I also need hidden, which is test W and B. Then P test is equal to non-PR max of output test axis 1 and R test is I don't know why I probably don't need hidden at all. I don't know where I put it. Yeah, I think I don't need this. And the rate of the test is classification rate. T-test, P-test. And that should be good to go. And let me just check it. Score, X-test, T-test. Oh,
Score doesn't return anything, right?
Huh? Thanks. Yeah. Okay, so I get around 97%. Okay. So what I have obtained this with this learning rate and this number of epochs. I was saying that it is completely the same if I do 1,000 epochs, because this is converging very soon to this value. So I am obtaining here the same thing. So what would be nice to do for you is to play with interplay between learning rate and number of epochs. So, for example, if this is much smaller, the learning rate here, instead of 10 to minus 4 is 10 to minus 6, then you expect that the convergence to this final performance here, it is obtained later, right? So let me put it here.
I can't hear, Brian.
You cannot hear, why?
I can still hear fine.
Okay. Okay, so let me probably, yeah, it's the same one, cost function. So what if I put here learning rate of 10 to minus 10? Learning rate is still, yeah, so probably this is a very simple data set.
Brian,
Yeah.
aren't you cheating a bit, because in the second run you are starting from the point of the WP?
That's why.
I mean
Absolutely.
this is an incredible amount of cheating. I mean, you should rerun the randoms, right, to make it more fair.
Yeah. That was a problem. Yes. Thanks. That is a problem. So let me restart and run all. Yeah. Okay, I forgot to since this is a global variable, yeah, I was cheating. Thanks. So let me see why it didn't do what I wanted. Okay, forget about this figure here. Restart and clean. No, I don't know. Okay, thanks, Jose. So here, obviously 10 to the minus 10 is too small. So 10 to the minus 6. Let me do the same. Yeah. So I need a lot of epochs, a lot more epochs, in order to arrive to the performance that I saw before, right? So there is an interplay here between learning rate and number of epochs here. If you choose it too small, then you will need a lot of epochs. Here, apparently, with 10 to the minus 4, it is enough to have 2,000 epochs. Yeah. Okay, so this is something that you can do in the sense that I will define it in the notebook and I send the notebook, but essentially, like you see the behavior of the learning rate as a function, of the number of epochs as a function of the learning rate you're choosing. Okay, so now let us see whether this model that we just implemented from scratch made sense, or it is comparable to some out-of-the-box model, like coming from scikit-learn. Okay, so let us do essentially the same thing that we did with decision trees, but now with another model. So we import from sklearn neural network, import MLP. This is from multi-layer perceptron classifier. MLP classifier. Is this okay? Yeah, okay. And then you go to this MLP classifier. You have a lot of parameters here. I think it is this. So this is the documentation of this method. So you have here a lot of parameters, but we want to compare apples to apples. So let us try to specify these parameters to resemble as much as possible, although I mean it is impossible to be exactly the same, but to resemble as much as possible what we have done from scratch. So first of all, number of layers here, hidden layer sizes here is 100 by default, but let us change that because we have only used 5. So let me hidden layer sizes. And why sizes? It is because this method actually implements a multi-layer neural network, in the sense that if instead of putting 5 here, which means one hidden layer with 5 units, I put here something like 5 and 10, it is interpreting that you have 2 hidden layers. The first one with 5 units, the second one with 10 units. Okay. 1 second, please. Here. Okay, so let us, for a moment, try to build up, to specify with the sklearn a network which is resembling as much as possible the one that we just did. And then another parameter here, activation ReLU, but there are many possibilities here. Default is ReLU, but I see that here logistic is the one that I've been using before, because it's just the sigmoid. So let us use the logistic activation equal logistic, because apparently this is a sigmoid. Then what other thing? Solver. Well, Adam solver is the state of the art of a stochastic gradient descent. So it is quite complicated. Let me see where is Adam. So yeah, so it is a quite complicated, complex model for optimization. We can either use this one or something which is more similar. We are not from scratch here. We didn't do stochastic gradient descent. We just did gradient descent, because if we were doing stochastic gradient descent, remember that we were just updating the weights with one of the elements of my cost function and not the whole cost function, which is what I have been doing right now. So let us use solver. We can we can put solver here, something which resembles as much as possible what we did, but it's not quite stochastic gradient descent. What else? Here, well, alpha, this is just something that is a penalty. This is just a penalty, like a regularization term in the regularization sense that we have been talking about in the previous lecture. So we are not using regularization. So I will use, let me see. Default is 1. I would like to shut off regularization, but I don't know if 0 is the correct. Probably 0 is the correct value here. So what I'm saying is that I have a doubt here of whether no regularization corresponds to alpha infinity or to alpha 0. It is not written here in the documentation. Okay, let me just not touch this this parameter, and then let's continue. Learning rate. Learning rate here is a possibility to do an adaptive learning rate. The default is constant, which is what I have been doing in my simple implementation. So if the default is constant, then another thing that I need to do is to say what is the value. If it is not constant, it is defined, the initial value is this one. But if it is constant, it is going to be the same value always. So let me just put here learning rate. And the learning rate here was for me 10 to the minus 4. And power t, there are other exponent, blah, 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 of the inverse. No, it doesn't apply for me. Maximum number of iterations, because why maximum? Because there is in all these scale-learn methods, there is a possibility to do something which is called early stopping. Early stopping means that if it arrives at some number, some epoch to some, if it doesn't change in too much, if it is not changing too much, it doesn't go all the way up to the maximum number of iterations, but it stays like below that. So this is early stopping, but since early stopping for us is false, and this is the value by default here, then I just specified this value. Max iter here for us, it was 2000, I think. Yeah. And that's pretty much it. Let me see if there are other parameters. Will shuffle. This is they shuffle the data every time for every epoch. Warm start. This is not applying to us, etc. Early stopping is important, but it is false, which is what we want, etc. So let us see how it goes with these parameters. And now it is a moment to feed it with the feed method of all these models in sklearn. T-train. I do this. Okay, it's taking a bit, but it should finish very soon. Okay, so it did something. Maximum iteration reached. Okay, so let me just. So I'm saying what it's saying here is that it's a warning. It's nothing serious. It's a convergence warning saying that given some criterion by default, it is realizing that there is some improvement after this number of iterations. But let us stick to it, and let us, after training, score. We compute the score on the test, and this is just 97. Okay, so 97 is exactly 97 that we got here. So we see that somehow what we have done makes sense. And let me see if I put 3,000 instead. So let me see if it improved somehow. I don't think so, but maybe. Okay, yeah, okay. Subleading improvement. Okay, it's not an important improvement, but still it is an improvement. Still, it is telling me that maximum iterations is not yet. So let me see. Okay, I will put 5,000 just to see whether it converges. Probably there's some verbose here that we can do verbose. Let me see what is verbose. I'm usually not using scale-n. I'm using my own implementations, but I mean, not from scratch, but with the TensorFlow. Yeah, I suppose that verbose is the way to go if you don't want to wait silently. Okay, so it didn't complain, which means that at some point before 5,000 iterations, it converged. So let me see, 98. Okay. So 1% better than our implementation. So this is more or less like validating our implementation in a way. So let us plot this finally. So in order to plot this, let me just, I think I have written, let me just create a linear space from mean of x, all the data, to max. Mm, 100 terms like this one. And I create the same for y, which is the second column of the input. So I'm just creating the grid here. So in order to create the grid, there is this method mesh grid. And then let me just stack it just to make a prediction. It's just a horizontal stack of this shape. -1 with 1. And the same with y. This is y. So I need this to stack it in this way in order to make my prediction. I call it here set, but it doesn't have to do with the output of the hidden layer. It's just the way it's just for plotting. This is just a prediction. It's full here, and I'm just reshaping this. Reshape to be the same as it has x. Okay, so predict here is the following. So let me just this method here, if I call predict of X test, name predict is not defined, so it's classifier.predict. What is giving me is a prediction, which is the Rmax for every point, right? So this is what prediction is about. So that's why I'm just reshaping this to be a column vector. So, and then I'm just plotting a contour of that. Plot contour, a field contour of X and Y and Z with some map here. Let me just not put this. And let me see whether it did something. Okay, 0. C map, plot contour F.
I think in mesh grid you have XX and Y instead of XX and YY.
Oh, yeah. Thanks a lot.
Yeah, but I think the problem is on the definition of XX. If you see the error.
Yeah. This is what I'm trying to. It is probably the fact that.
I think, Brian, is when you put numpy.min in X, you have to put 2 indices and you only vote 1. Yeah, I think you have to put.
Yeah. Like this.
Yes.
Okay. Thanks. Okay. Yeah. So just let me before showing this, let me just put points just to see if I have an idea. Scatter. I'm putting the training points. Strain 1. And with the color, let me just put the color equal to the train. Okay, so it's yeah, the colors are not the best. So let me put but this is just statics. PLT color map, get CMap, blues. Let me see if this is better. Okay. Okay, it is showing a bit better now, the contrast. So here the this is more or less what is the decision boundaries that the model got. And you can play with that again in the same way that you can play with in naive Bayes with the original data. Here you can do the same with this data. So this is more or less linearly separable, not that much. I mean, not completely linear. So you see, let me just hide again the points. So there is some curvature here of the decision lines, but as you consider clouds of points of different classes which are more different from each other in terms of variance, these non-linear boundaries should become more and more evident. Okay, so yeah. So what I suggest you to do at this point is to start playing with. So let me just put it here. So one is play with learning rate. So let me put here homework. You can start playing with learning rate versus epoch, number of epochs. As a function of learning rate, but also you need to play now with the number of units in the hidden layer. right? This is also a hyperparameter. For example, let us rerun the whole thing with instead of 5, let us rerun the whole thing with what to put here. I don't know, 20. So let me see what is 20 doing. Start, I don't know. Okay, so it's a bit better, no? So before we were obtaining 97, now it is 97.3, maybe, but not too much more. So the gain here is the gain here is not that significant, and it is because this is a simple data set. Okay. Here I've got how many? 97 again. Yeah. No, here what I need to do is to put 20 just to compare the performance of sklearn. Okay, more or less the same. Okay, so let's play with that. With these two parameters, let's say. And what else? What you can do also? What you can do also is to in sklearn. Finally, we put a third thing in sklearn MLP classifier model. Increase number of hidden layers to see whether you gain something extra. Is there any question so far? Because I will stop here.
I have something that is more of a posterior question. So imagine that you do all this fit, and this is for a function, but this is going to be part of something else. You need to pass this function, you need to pass this neural net to your collaborators.
Okay.
I mean, you just give them, you tell them, okay, these are all the matrices, and then you just do all the chain function and so on, or there's something that, let's say, either scikit-learn or Python, there's a sort of common standard to distribute this information.
Well, yeah, what you're referring to share the training model.
I just want, once I train the data, right? I have my data set, I split it, I train it, I have a function which is the output. I want to share the neural net. I want to give the neural net to someone else because this is an input for something else.
Right. So what you typically share is the neural net with the optimum parameters. Okay.
Yes, and this is something that, for instance, scikit-learn has some function that it outputs that in which kind of format. So you.
Yeah. So in sklearn, you get you have this get params here.
Mm-hmm.
So let me just get it. Get params. If I use it, let me because it's going to be huge for. Hidden layer size is 5. No, what is this? Oh no, this is another notebook. Let me go back to 5. Let me just train, and if I call get params, it should do something. Classifier get params. Okay, so this is just a dictionary, but no, this is not get params, right? Set the parameters of the estimator. No, wait a second. How was this? Parameters, update the model. It was not get params, but it was another thing. Maybe get weights or something. I don't remember now. How was it? There is a built-in function here for all these methods that allow you to. So if I get only these two.
If I recall correctly, there exists some kind of function which should output your entire set of weights to a CSV or something, which can also be loaded in again, right?
Yeah. But I just don't remember now how to do it in the sklearn.
Okay, I mean, I can check it. I didn't know if this functionality was written.
It is.
Okay.
It is definitely is. And also what, I mean, of course, I mean, if you use it just for out of the box thing, then they allow for a lot of information to get extracted. But obviously here, if you do it more manually, I'm not saying that for a deep neural network you need to do this by hand. Of course not. So present I'm working with other libraries like TensorFlow. But what I'm saying is that if you go to a lower level code, of course you will have access to this information, right, from by hand. But yes, I mean, for example, now my W was before, or my B was before this, and if I print B again, it will be another thing because it has been updated after that many iterations. So I immediately can extract all these parameters, and then I just give the architecture, which is just the way you build your output. In any case, this is an analytical function at the end of the day, right?
Right,
So,
but of many parameters. So somehow passing it around can be a bit complex. I wasn't sure how you pack such output.
yeah. So,
right? I just one thing. I haven't seen in the archive. You know, in the archive you can add data to your publications. I never seen anyone attaching a neural net. Okay, I see people attaching data tables. I see people attaching code, but I haven't seen that. So this is why I don't know if there's a sort of.
It is definitely is. So there is a built-in function. I need to find it now. First sklearn, which I have done this some time ago, but now I forgot. Of that allows you to get all these parameters.
Okay, thanks.
And once you do this and you specify how to use these parameters, like specifying your model, then you're good to go, and you can without training you can actually reproduce the performance on some set of test data, let's say. I don't know, sklearn get weights perceptron. I don't know how determine random generation. Model coefficients. That was the thing. Model coef. Let me see. Classifier coef. Is this with like this or what? Yeah. Look at it. So those are the weights W and V. But then probably there's something similar for bias or something like that. No. Print there. Okay. I don't know. There is also something similar for the bias. It is not. I don't get it. I'm guessing here, but definitely this is here. This is like a W, and this is V. And similar thing for the bias. Okay.
Yeah,
you just have to search for it. But this is the information you were looking for, right?
Yeah, I mean, essentially, I think the best way to pass it to someone else is to pack it in a sort of Python code where you output such table and then you just reveal the function with these
Absolutely.
coefficients, right? That's
yes.
Probably okay. I thought that maybe there was a more compact form to move this around, but it's fine. Okay, no worries.
Yeah. Okay. Any other question? So just before finishing, in order to do like okay, there is here this code that allows you to put many hidden layers, and this is convenient, etc. There is not only scale-learn to do that. There is something called fast AI, I think. Fast AI. I learned this from one of you, from Gabriel. So this is also a code for that. I don't know the code at all, so but you can explore it because it is probably giving also good results. But essentially, the way in which developers of or if you want people doing machine learning research, like I'm trying to do now, deal with this is with the TensorFlow or PyTorch. So TensorFlow is just a library for automatic differentiation. So you give given a function which is a beast, a function of many parameters, it is just a way to a library for making derivatives automatically. It is just that it has a lot of methods to build neural networks, and also PyTorch. But that would be probably the way to go. If you want to have your deep network, etc., this would probably be and there are a lot of tutorials in the internet for that. But okay, this is not a course about deep learning. This is just a generic introduction to neural nets, and I think we are good at this point. Okay, any other question maybe before we close the session? Okay, right. If not, let us close here, and then we meet tomorrow again.
Okay, thank you.
Thanks. Bye bye.